Okay, this second example is about an inclined plane or a ramp. This is one of the most common examples of forces in 2 dimensions that you will find in physics, and it's very used in real life. So it's a very important example to know how to solve. So like last time, we read the problem that is in words and numbers and we transfer it into a diagram and then a free body diagram more specifically. So what we have is an inclined plane or a ramp that is inclined or slanted 30 degrees. And on top we have a block of mass 4 kilograms, and there is a coefficient of friction between the block and the ramp of 0.10. Kinetic friction coefficient is 0.10. So what we're looking for again is the acceleration of the block down the incline. We want to know if the block will start moving or if friction is too big, and if it is, then if it will start moving, then at what acceleration. So we draw it first. What we do is we draw our inclined plane at an angle of 30 degrees. So we know that inclined planes and ramps are always right triangles, and the 30 degree is here. So that's what the problem means. And we draw our little block somewhere in the middle of the incline, wherever you want. This is our little block. Okay, so that's what we know until now. And the information that we were given in the problem, apart from the 30 degree angle, is that the mass is 4 and the coefficient of kinetic friction is 0.10. Okay, so the steps are exactly the same as the previous problem, which are first draw all the forces on the diagram. So again, we need to remember the first force and the force that we always put on every diagram is the force of gravity, or the weight, which always points downwards. So we pull it from the block downwards and we call that Fg. So now again, the force of gravity is mass times the, let's put it, I think it will look more organized if I put it down below. So what we know is that the force of gravity, or the weight, is mass times 9.8, mass times g. So that is 4 times 9.8. We can put that in your calculator. Let's see, 4 times 9.8 gives us 39.2 newtons. So the weight of a block of mass 4 kilograms is 39.2 newtons. That is Fg. We can put it here now. 39.2 newtons. Okay, that's one of the forces. The other force that we always have when the block is on a surface is normal force. But this is what I was talking to you about, that normal force will not always be upwards, but it will be perpendicular to the surface. So because our surface is 30 degrees slanted sort of to the right from horizontal, then our normal force will be 30 degrees slanted to the right from vertical. So it's going to be 30 degrees to the right of the vertical. And that also means it's going to be perpendicular to the ramp. So it's going to look maybe something like this. This is normal force. And we don't know the value of normal force either. If the ramp had no friction, that would be the whole free body diagram. There's nothing else touching the block, so there are no other forces acting on it. But since there is friction, then we add an extra force, which is, of course, friction. So the block would accelerate down the ramp, so friction to stop it would be up the ramp. So it has to be parallel to the ramp, or parallel to the direction of motion, but upwards. So it has to be also like making a 90 degree with normal force, which means something like this. Friction force. That's what we've got. So actually, no matter how many times you do this, the free body diagram of a block and a ramp will always look sort of like a Y, like the letter Y, because it's two forces sort of in diagonal and one force that is always downwards. So this is the basic image of how a free body diagram for a block on a ramp looks. So that's it. We have all of our forces There's nothing else acting on the block. We've done our free body diagram. But now we need to move on to the following step, which was, if you guys remember, to divide any forces that are not in the same direction as the movement into its components. So the movement is going to be up and down the ramp, right? In this case, only down the ramp, but in this direction of motion. So the force that is not parallel nor perpendicular to this direction is actually weight, the force of gravity. So in ramps, in inclined planes, we will always divide into components the weight. So now it's not going to be normal force, it's not going to be friction force. The force that we're going to divide into components is the weight. That will always be the case in inclined planes. So if you can imagine, the components will not be horizontal and vertical anymore. They will be parallel to the ramp and perpendicular to the ramp, because it's sort of as if we were looking at a problem slanting our heads to the right 30 degrees. So now the two directions will be down the ramp and like across the ramp. Yeah, so we can call this parallel to the ramp. So this is the component of the weight parallel to the ramp, which is usually drawn as two parallel lines. And this one we're going to call the component of the weight perpendicular to the ramp, which is drawn sort of like a backwards T, like that piece in Tetris that looks sort of like a backwards T. So parallel and perpendicular. So again, we can calculate these two using our equations, cosine and sine. So this you can memorize, or you can look at it geometrically, whichever you prefer, but the parallel one will always be sine, and the perpendicular one will always be cosine. So that's something that people sometimes forget and get confused with. It's just a matter of memorizing which one is with which. So what we're going to have is that the parallel component of the weight is the weight times sine of the angle, which is 30 degrees. I hope you can see this color. And the perpendicular one is going to be the weight times the cosine of 30 degrees. So again, we put these things in the calculator, and the weight, remember, is 39.2. So for the first one, for the parallel, we get 39.2 times sine of 30, which gives us 19.6 newtons. And the perpendicular component will be 39.2 times cosine of 30, which will give us 33.9 newtons. So there we go. So this parallel one is the 19.6, and this perpendicular one is the 33.9. Okay, after we have this information, we can do what we did last time and divide the problem into the two components, the parallel and the perpendicular component. So the motion of the block is going to be in the parallel component, right? It's going to move parallel to the ramp downwards. So what we do first is the other one, which is the perpendicular component. So we start with perpendicular, whose symbol is this little backwards T. Perpendicular. So the forces that we have perpendicular, and remember we can ignore our weight already because we divided it into two components, so we can ignore it from now on. So perpendicular, we've got these two, the perpendicular component of weight and the normal force. So again, sort of upwards or away from the ramp is positive, which means we have positive Fn. So again, we're going to do our equation. Net force is mass times acceleration in the perpendicular direction, and the net force is the normal force in one direction. And opposing the normal force is this component, so we subtract that component, which is 33.9. And there's no more forces in perpendicular, so we equal that to mass times acceleration. mass was 4 kilograms times acceleration, and the perpendicular acceleration, as we said, is 0, because the block won't fly off the ramp perpendicular to it, and it won't crash through the ramp either. So it's not going to move perpendicularly to the ramp. So we just put a 0 there. So again, just like the previous problem, we can solve for the normal force with this information. So what we do is pass this to add to the other side. This is a 0, so we get that normal force is 0 plus 33.9, which is just 33.9. So this is actually a result that you can remember, that the normal force will always be equal to the perpendicular component of weight. But you don't have to remember it. You can just use Newton's second law, like we always do, and find it for yourselves. So that would be our result for the normal force, and that's all we can do with perpendicular. So again, we move on to parallel. So we end that there and move on to parallel. So parallel is the two straight lines, and we use our same equation as always. Net force is mass times acceleration. So now, which forces are parallel? Well, we have two also. We have the parallel component of weight, which pulls the block downwards, well, down the ramp. And we also have friction force, which stops it and goes in the opposite direction. Again, we can ignore the weight because it was already divided into its two components, so we don't need to worry about it anymore. We just worry about the four forces that we're left with. So we take down the ramp as the positive direction so that we get a positive acceleration because the object is going to go down the ramp. So we say that this one is positive, 19.6, the parallel component of the weight. And we subtract the force that opposes it, which is friction force. So again, friction force, we have our equation. So remember, friction force is the mu times the normal force. So mu was given to us in the problem, it's 0.10. And we multiply that by our normal force, which we just got up here. So it's basically the same procedure as the last problem. So this whole thing is friction. So we had the parallel component of weight, subtracted friction, and those are the only two forces acting parallel. So we equal that to mass times acceleration. Our mass, 4 kilograms. And our acceleration, we have no idea yet. So we put it as A. So again, we have all numbers on this side, so we can solve that right now. So we get 19.6 minus 0.10 times 33.9, and we get 16.21. 16.21 is equal to 4A. And again, to solve for A, we pass the 4 to divide on the other side. So we get A equals 16.21 over 4, which is going to give us 4.05 meters per second squared. And that's it. That's our result. And it says that the block will actually move. Friction force is not big enough to stop it from moving, and it will start accelerating at 4.05 meters per second squared down the ramp because we got a positive answer. So that's the acceleration of the block down the incline.